we have a couple of days to cover 1.6, so we'll get as far as we can in the workbook today, and then there's no class on Monday. So next Wednesday we will continue with finishing 1.6. There's a worksheet that I posted on Canvas that's going to be due this Sunday, or depending on how far we get today, I may change that due date. But let's just see what we're working with here. In 1.6, we're going to learn how to graph functions using shifts, reflections with the XY axis, and then we're going to talk about even odd functions, and then we're going to look at compressions and stretches, and then we're going to combine all of those things together to kind of graph functions using the horizontal shifts, vertical shifts, compressions, reflections, and all that. So you watched the lecture videos for these, hopefully. So I'm going to go straight to an example here. And I'm going to talk about some of the key identifying features of how to identify transformations. So first one says use the function f of x, which is represented above. So we're using this function f of x up here, this graph, to graph g of x, which is f of x plus 3, and h of x, which is f of x minus 2. When we think about f of x and g of x or h of x, whatever, those are outputs, right? We've replaced f of x with y in the past, so this is an output as well. So what's happening here is we're adding 3 to the y value of a function, right? So if you add 3 to the y value is going to affect our graph up and down. So it's going to shift our graph up and down, and adding 3 to all of the y values would shift our graph up. So this plus 3 you can identify as up shift of 3, or a shift up of 3. And we'll see that in the table here when we start doing this. We're going to take the f of x values from the table above, and we're going to add 3 to them. So the first one would be 3 plus 3 equals 6. The next one is going to be a 1 plus 3 equals 4. For 0, f of x was negative 1, so negative 1 plus 3 equals 2. When x was 1, y was negative 3 plus 3 equals 0. And negative 1 plus 3 equals 2 again. And not 3, sorry. 1 plus 3 equals 4. So we get these f of x values here, right? And then we add 3 to them, because that's what g of x is just the y values added, or 3 added to the y values. And so we get these new y values, and we can plot those on the graph. Negative 2 is 6. Negative 1 is 4. 0 is 2. 1 is 0. 2 is 2. And 3 is 4. So we get this graph with those points, and we see that looking at the original graph, the blue graph above, we've just taken this whole thing and just shifted it up 3, right, to get to this one. So it should have the same shape, the same openness of the V, the same exact number of points, same orientation and everything. It's just shifted up 3. Okay, we'll leave this one. We'll leave this one for you to do. On the other hand, if we see something like this, where we're starting with the same function f of x, the one from up here, the table, and we're looking at f of x plus 2, this means we're going to do g of negative 4, because that's our x value, which is, I guess I don't need to write that. Let's just write it as f of negative 4 plus 2, because my x is 4, or negative 4, right? So I plug in negative 4 into here. That's f of negative 2, which we can look at the table to figure out what f of negative 2 is, and that is 3. Right? So we pull f of negative 2 from the table. This is 3. And so we continue. F of negative 3 plus 2 is going to be f of negative 1, which from the table is 1. F of negative 2 plus 2 means f of 0, which from the table is negative 1. F of 1 is negative 3. F of 2 is negative 1. And this is 1 from the table above. So when we graph these, negative 4 comma 3, negative 3 comma 1, let's put those on the graph. Negative 4 comma 3, negative 3 comma 1, negative 2 negative 1, negative 1 negative 3, 0 negative 1, and 1 1. Alright, so we get this graph here. What does it look like the shift was from the original graph to this graph? What kind of shift do we see here from this original one to this?
It shifted 2 to the left.
Yeah, so left 2 was the shift there. We don't need to fill out more of this table because we don't have table values for that. For the second part, you minus 1. So negative 1 to 4. For the other one, you're not going to fill out the first 3 there because you're not going to find values in the table for those first 3 if you tried. Right, so in general, what does that mean? That means that we can look at a function and determine what kind of shifts are happening, what kind of translations are happening, just from identifying where the number is added or subtracted. So if you have a whole function and you're adding a value, this k could be positive or negative. If you're adding a value to the whole function, then this is going to be a vertical shift. So this plus k here outside of the function is a vertical shift. And then if k is positive, the shift is up. If k is negative, the shift is down. These are kind of just blanket statements for all functions. And then for the horizontal shift, the number that's affecting our function is going to be kind of attached to the x in the parentheses with the x, right? So if you're modifying the x directly with a value h, notice that this is a minus h in standard form. So when h is positive, the graph shifts right, and if h is negative, the graph shifts left. Now this gets a little bit weird when you're actually looking at a function because this standard form is written as x minus h. Okay, so if we see, for example, is there an example? No. If we see, for example, x minus 4 squared, that is our function, let's say, g of x, and our original function f of x is just x squared. So this is our parent function that we're modifying. This is essentially just a translation of the original function, right? We still have the quantity squared here. All we've done from f to g is this minus 4 here. So this minus 4, first of all, is it going to be a horizontal or a vertical shift? What do we think?
Horizontal.
That looks like it's going to be horizontal because it's in the parenthesis with the x. The x is being affected directly. The minus 4, is that going to be a left or right shift?
Right.
Right, good. How do we know that? Even though it's kind of weird because it's minus?
Because the h is in standard form. In standard form, it's negative.
Good. So this minus matches the standard form of how we've learned or how we've defined these shifts. So this 4 here means the h is 4, which means we have a shift right. 4 units, right? Okay, so just be careful with that one because the vertical shift is pretty straightforward, right? If you add a number to a function, it's going to go up. If you subtract it, it's going to shift down. Whereas the horizontal shift is a little bit backwards. If you subtract a number here, like minus 4, that's going to shift your graph to the right. If you want to think about it as the vertical shift shifting the actual function and the horizontal shift shifting the xy axis in the background, that might help if you find yourself confusing things. This shifts the function, like the actual blue line, right? If I take this blue line and I shift it physically up or down, that's what the vertical shift is doing. Whereas the horizontal shift is shifting the xy plane behind the blue line, right? So if I see like a minus h here, that's shifting the blue, it's not the blue line, it's shifting the whole axis to the left, which results in the v-shaped graph being shifted to the right, right? If that confuses you, then don't worry about it. Just memorize it as is. But I feel like that helps if the whole negative h thing confuses you. I feel like this might help understand why that's happening. Cool. Are there any questions on vertical horizontal translations? Okay. You guys can work through these. Let's talk about reflections, and I think like these are good examples for you to do. Let's talk about how reflections are defined, kind of like how the translations were defined. If we start with the function f of x and we multiply the x value by a negative, that is a horizontal reflection over across the y-axis. So if I take all of the x values and I multiply them by a -1, you can imagine that, let's say we have a graph. Let's say it looks like this. Let's say the graph just looks like that, right? It's the kind of like a ray. If I were to take the x values on this graph, like this x value, for example, let's say it's like 5, 1. If I were to make the x value negative, it would now become negative 5, 1, and my point would end up being over here, right? It would reflect over the x-axis to over here, and each point would reflect over the x-axis, and we would get an image, a mirror image of this original graph reflected over the y-axis. Did I say x-axis? I'm sorry if I said x-axis. The x values get reflected, so they go over the y-axis. So this point here is kind of like an x comma y, and then this point would be a negative x, negative of that x with the same y. All right, so that's how horizontal reflections work. Instead, if we were to start with the function f of x and multiply the y values, or the f of x values, by -1, then we have a vertical reflection on our hands, and that's going to reflect our function over the x-axis. So if we have a graph like a parabola, for example, right, and we take the points on here that are x comma y, and I convert that to x comma -y, it's going to reflect across this axis, and we'll have x comma -y down here, and this graph would just reflect over the x-axis. Any questions on reflections? I guess I'll write a couple of examples here. Starting with f of x equals x squared, we'll say that's our parent function, right? How would we reflect over the x-axis? Where would I put a negative for this? So let's say g of x is going to be a reflection over the x-axis. How would I write that in terms of x squared?
Negative x squared.
Good. What about reflect over y-axis? You're just gonna say the same thing, but we're gonna write it a little bit differently here, right? We still want to do negative x squared, but we actually want to multiply the x by a negative, not the x squared, right? So we're gonna do negative x quantity squared. Right, those are two different things. One of them is multiplying after the square happens. One of them is multiplying before the square happens. Anything interesting about either of these functions? Or I should say, what is interesting about one of these functions?
Is it h of x equal to f of x?
Yeah, why?
Because, I mean, after you square it, it'd be the same values.
Good. If you square negative x, this is a -1 technically in here, right? -1x. And if I square the -1 and if I square the -1 and I square the x, the -1 squared is just going to give me +1, and we end up back at x squared here. Which is the original function, right? So that's kind of interesting that we reflect over the y-axis and we get the original function. Is that surprising though? Or I should say, why is that not surprising? That reflecting over the y-axis got us back to the original function. Why is that not surprising?
Because parabolas are symmetrical
About the
at the y-axis.
good, because a parabola looks like this, right? If I were to take that and reflect it across the y-axis, it would just be switching these two halves of the parabola, right? We have something U-shaped, we flip it around, it's still U-shaped, right? If I rotate this around this way and this rotates around that way, if we reflect it across this vertical line, it's already mirror image of itself, so it lands back on itself when you reflect over the y-axis. So that actually leads us nicely into the next thing we're going to talk about, because functions like this, where you try to reflect over the y-axis and they don't change, are going to be even functions. So we're going to talk about even and odd functions next, which are functions that have certain kinds of symmetries. Oh, I kind of got ahead of myself. I guess we're doing that here, but you guys can graph this one here. I want to talk about this statement here is important. An even function is symmetric about the y-axis, which is what we just talked about. So y equals x squared is symmetric about the y-axis, which means it is even. Right? There are other examples of this x squared. The parabola is not the only one that is symmetric about the y-axis. And then we're going to look at y equals x cubed, which is this shaped graph. You will... Why are we graphing that? I don't want to graph that. Negative of f of negative x. Interesting. I don't think we want to graph that. I think I'm going to change this problem, because that's not... what do we want to do here? We want to start with x cubed. We want to graph... I think we still want to graph... We don't want this negative here, so get rid of it. We just want f of negative x. No. We want to
I think in the video graphing negative f.
Negative f of negative x?
Is the same as the original function.
This is the same as the original function?
I believe according to the video.
Okay. I just don't like, that's not... I feel like this example is not very useful, but we'll leave it as is. I don't want to mess with it then. You can if the video already did this, then you can if you did it already, then good. If you're not, you can do it when we go to breakout rooms. You're gonna look at what happens when we do negative of f of negative x, but in general, an odd function is symmetric about the origin. Now, origin symmetry is kind of weird because you're reflecting about a point, right? It's kind of easy to look at a parabola and say that there's a mirror. If there's a mirror here, then it's a mirror image of itself, right? Because we see the same points on the left and right. Whereas if you're symmetric about the origin, you kind of have a mirror at a point, right? So this point at the origin is acting as a mirror. So when I take this point down here, I draw a line to the origin and I continue going to the other side, I find its mirror image on the other side, right? So every point on here is reflecting about the origin to another point on the other side. So this is an example of a function that is symmetric about the origin because every point has its counterpart on the other side of the origin, right? Reflected across the origin. Let's talk about how to determine whether a function is even or odd using algebra. So looking at a graph, we can say, oh, okay, this looks like it's symmetric about the y-axis, so it's going to be even, or it's symmetric about the origin, so it's going to be odd. But if we don't have a graph, if we just have some function that we're starting with, like the absolute value function, for example, we should be able to do it algebraically as well. So let's look at these. A function is called an even function if for every input x, f of x is just equal to f of negative x. And then we already said that it was symmetric about the y-axis. And then for odd functions, we have f of x is equal to negative f of negative x, which means that they're symmetric about the origin. So in practice, how this works is we're going to test. Let me rewrite a different version of this one that is more useful, I think. For odd functions, we like to say that negative f of x is the same thing as f of negative x. That's another version of the same thing. The reason why that one is more useful is because we have this f of negative x that's the same between the two, which means we just have to look at f of negative x and the way that behaves to determine whether it's even, odd, or it could be neither even nor odd if it doesn't behave in those two specific ways. Let me show you an example of how to do this algebraically. I will do part B, and you guys can work on A and C. So what this means is we check g of negative x. So we plug in negative x, and we see what happens to the function. One of three things are going to happen. Either we're going to get some stuff, and then we're going to simplify it down, and it's either going to be g of x. We're either going to get back to the original function that we started with, or we're going to end up at negative of the original function that we started with. Or we're not going to end up at anything that relates to the original function in a nice way like that, right? And depending on which one of those three things happens, the answer is going to be even, odd, or neither. Looking at the box up here, if I start with f of negative x, or g of negative x in our case, and I end up back at the original function, that means the function is even. Right? Instead, if I start with f of negative x, or g of negative x in this case, and I end up back at the negative of the original function, then my function is odd. Right? And then if it doesn't fit into these two categories, where it's exactly the same as the original function, nor exact negative of the original function, then we say neither. Right? So neither is an option. A function can be neither even nor odd. So let's take a look at this example here. If I plug in a negative x, how do I do that? How do I plug in negative x into a function? Or someone tell me what to write here when I plug in negative x.
It's like a negative sign on all the like input x value.
Okay, so the first one would be negative x cubed, right?
Or explain it.
Right?
Yeah.
Did I do that right? Okay. And then 2 times negative x. All right, so we replace the x's with negative x's. What happens when we cube a negative one? Or a negative value?
Is it a negative?
It is negative, which means this is the same thing as that without the parentheses. And then this is a positive 2 times a negative x, so we get a negative 2x as a result there. Now let's remind ourselves what we're trying to get to. We're either trying to get, or we're seeing if we can get to the original function back to the original function, or back to a negative times the original function. Which one does it look like we're going to get to?
Negative times the original function.
Yeah, so to easily see that, we can factor out a -1 from this expression and write this as x cubed plus 2x in a parenthesis. Right, if I factor a -1 from that, this thing that we have in the parenthesis is the original function, which means we got negative of the original function g of x. This equality here, this g of x equaling negative g of x, is the identifying factor of an odd function. Is that what the question was asking for? Kind of. It didn't say it that way, so we should probably say g is odd. So it is symmetric about the origin. I mean, we could just shorthand that and say G has origin symmetry. Are there any concerns about why the negative x cubed becomes this negative x cubed? Why we can drop the parentheses there? Are there any questions about like when we can just drop the parentheses and keep the negative, and when we don't do that? No concerns. Does anyone want me to show you why that happens? Okay. If you guys are completely confident in your abilities to evaluate those negative values, then we are fine. You guys can check what happens with these other examples. We will move on to... Actually, are there any questions on the even odd situation? How to determine, using these two statements, whether the function is even or odd? Okay, let's move on to, hold on. I don't really want to move on to stretches and compressions. Let me see how much is left. We have stretches and compressions, and then combined transformations. I think I'm going to stop there for the recap for today.